Namaskaram. In last class, we have discussed evaluation of real integrals of the type integral 0 to 2 pi f of cos theta sin theta d theta. In this session, we will consider a real integral of the type integral minus infinity to plus infinity f of x dx, where f of x is a ratio of two polynomials, capital F of x by g of x. And there is a restriction for degrees of these two polynomials. The degree of g of x is at least 2 units higher than degree of f of x, and no zeros of g of x lies on the real axis. That means if degree of x is equal to 1, then degree of g of x is at least 2 units higher. At least 2 units higher. That means degree of g of x is greater than or equal to 3. It should greater than or equal to 3. Okay, at least 2 unit higher. Okay, for example, if f of x is equal to suppose some x plus 1, then what about g of x? The one possible polynomial of g of x is at least degree 3. So x cube plus some x square plus 1. Clear? So its degree is at least 2 units higher. Here degree of the numerator is 1. Here degree of denominator is 3. Clear? And we have one more condition. No real zeros of g of x lies on the real axis. That means if you take suppose we consider f of x as 1 by x square minus 1. Here degree of numerator is 0, right? It's a constant function, and the degree of denominator is 2. So it satisfies this condition. G of x is at least 2 units higher. Degree of here degree is 0, here degree is 2. So at least 2 unit higher. Then what about the second condition? The second condition is no zeros of g of x lies on the real axis. What are the zeros of g of x? Here f of x is 1 and g of x is x square minus 1. So what are the zeros of g of x? So whenever g of x equal to 0 implies x square minus 1 equal to 0. So x square equal to 1. This implies x is equal to plus or minus 1. So this g of x has zeros which lies on the real axis. So this is not allowed. Clear? So this function is not allowed. This function satisfies the first condition. First condition means degree of g of x is at least 2 units higher than numerator. But it doesn't satisfy the second condition because this function has zeros on the real axis. Clear? So these are the two crucial properties of f of x and g of x. Degree of g of x is at least 2 units higher, and no zeros on real axis for g of x. So for example, you can say another function. Suppose f of x is equal to 1 by x square plus 1. This is allowed. It satisfies the first condition as well as second condition, because what are the roots of this new denominator? X square plus 1 equal to 0 implies x square equal to minus 1. So roots are plus or minus I. The square root of minus 1, that is plus or minus I. So no real roots for this g of x. So this function is allowed. Okay. So I think it is clear. Okay. Under this assumption, the integral minus infinity to plus infinity f of x dx is equal to 2 pi I into sum of residues of f of z. Okay, you simply replacing x by z, that is f of z. Okay, and what about the summation, where this sum is runs over all the residues of f of z at the poles of f of z in the upper half plane. Okay, so in last example, our function f of x is 1 by x square plus 1. Okay, in this case, what is f of z? F of z is 1 by z square plus 1. Then what are the poles of this function? By putting z denominator 0. So when z square plus 1 equal to 0 implies z is equal to plus or minus I. So what about these poles? They are simple poles. We can write this as 1 by z minus I into z plus I. So they are simple poles. Okay, and which poles belongs to in upper half plane? Which singularities belongs to in upper half plane? Okay, so I is somewhere here and minus I is somewhere here. So it is clear that minus I is not belongs to upper half plane. So we have to find only a residue at the pole I, because this only one singularity I is belongs to upper half plane. This pole minus I is belongs to lower half plane, not in upper half plane. Okay, so in this exam, in this problem, means f of x is equal to 1 by x square plus 1. Then what about this final answer? This integral minus infinity plus infinity 1 by x square plus 1 dx is equal to 2 pi I into sum of the residues where summation runs over all the poles belongs to upper half plane. We have only one pole on the upper half plane. So 2 pi I into residue at z equal to I of f of z. That's all. Clear? So this is the idea of this result. Okay, now we will solve a problem. Okay, evaluate integral 0 to infinity dx by 1 plus x raised to 4. Here our integration ranges from 0 to infinity, but our standard form is integral minus infinity to plus infinity. But here the inside function is f of x is equal to 1 by 1 plus x raised to 4. It is clear that this function is even, right? Because if you are replacing x by minus x, then what happens? If you are replacing x by minus x, this is 1 by 1 plus minus x raised to 4. This is same as f of x, 1 by 1 plus x raised to 4, isn't it? So this function is even. Okay, so what about integral minus infinity to plus infinity 1 by 1 plus x raised to 4 dx? We know that for even functions, integral minus a to plus a f of x dx. If f of x is even, then integral minus a to plus a f of x dx is equal to 2 times integral 0 to a f of x dx. Using this property, we can write this as 2 times integral 0 to infinity 1 by 1 plus x raised to 4 dx. Okay, so our required integral is this one, integral 0 to infinity 1 by 1 plus x raised to 4 dx, that is equal to 1 by 2 times this integral. Clear? So this is equal to this, in our required integral is equal to 1 by 2 times this integral. Okay. Okay, so first we are going to evaluate this portion, this part, integral minus infinity to plus infinity 1 by 1 plus x raised to 4 dx, using our last result. Okay. Okay, in this case, what is our capital F of x? Capital F of x is 1 and capital G of x is 1 plus x raised to 4. It is clear that it satisfies the degree criteria, because degree of f of x is 0 and degree of g of x is 4. So degree of g of x is at least 2 units higher than degree of f of x. Okay. Next we have to check whether what are the roots of this denominator function. So to find the roots, we consider this equation, and this implies then how to solve. Okay, anyway, we have to find the complex roots, all complex roots of this equation. So we consider the corresponding complex equation, that is z raised to z raised to 4 equal to minus 1. We have to find all complex roots of this expression. Okay, so we know that minus 1 is in polar form, that is e raised to I pi, e raised to I pi. What is e raised to I pi? That is cos pi plus I sin pi. Cos pi is minus 1 and sin pi is 0. So this is e raised to I pi is minus 1. Also, what is the periodicity of e raised to z? We know that e raised to z is equal to e raised to z plus 2 pi I, because we can write this as e raised to z plus, sorry, e raised to So this is equal to e raised to z into e raised to 2 pi I. And what about e raised to 2 pi I? That is cos 2 pi plus I sin 2 pi. We know that sin 2 pi is 0 and cos 2 pi is 1. So this value is 1. Okay. So in general, e raised to z is equal to e raised to z plus any integer multiple of 2k 2 pi I. That is 2k pi I. We can easily verify that e raised to 2k pi I is 1. That is cos 2k pi plus I sin 2k pi. Sin 2k pi is always 0 and cos 2k pi is 1. Okay. So that's why the period of e raised to z is 2 pi I. Okay. Anyway, here we can write this as e raised to I pi plus 2k pi I, where k is an integer. Actually k is an integer. Okay. So this is equal to e raised to, here I pi is common, so this become 2k plus 1 into pi I, where k is an integer. Actually k is an integer. It may be positive, negative, 0, whatever be. So now we have an equation z raised to 4 is equal to like this. So what about z? So by taking the fourth square root, z become e raised to 2k plus 1 pi I by 4 where k is an integer. Okay. But whenever k equal to 0, so suppose k equal to 0, what happened? So whenever k equal to 0, this become e raised to pi I by 4. And when k equal to 1, this become e raised to 3 pi I by 4 and is at 3. That is corresponding to 2. And k equal to 2, this is 4 plus 1, 5. So e raised to 5 pi I by 4 and z4 is corresponding to k equal to 3. That is 7 pi I by 4. E raised to 7 pi I by 4. Geometrically, these complex numbers are like this. This is, suppose we consider a unit circle, because modulus of these complex numbers are 1. If you take the modulus, then this is all the modulus of all these complex numbers are 1. So all these complex numbers belongs to the unit circle. And first argument is pi by 4, so somewhere here, and next one is 3 pi by 4, so here, and this is 5 pi by 4, and this argument is 7 pi by 4. Okay, so this is our z1, z2, z3, z4. Okay. Whenever k equal to 4, what happened? This is 8 plus 1, 9. So e raised to 9 pi I by 4. So 9 pi by 4 is here. Okay. So whenever k equal to 4, the complex number corresponding to k equal to 4 is same as the complex number corresponding to k equal to 1, k equal to 0. Similarly, whenever k equal to 5, that complex number is equal to the complex number corresponding to k equal to 1. That means z2. Okay. Similarly, the root corresponding to any other k will be one among these four roots: z1, z2, z3, z4. Okay. So the four complex roots of x square plus 1 equal to 0 are z equal to e raised to 2k plus 1 pi I by 4, where k equal to 0, 1, 2, 3. Okay. Okay, so this x raised to 4 plus 1 equal to 0 has 4 roots. These are the 4 roots, and geometrically the positions of these 4 roots are here: z1, z2, z3, z4. It is clear that only 2 roots, z1 and z2, belongs to upper half plane. So next we have to calculate the residue of this function. F of z is equal to residue of f of z is equal to 1 by 1 plus z raised to 4 at the poles z1 and z2, because they are only singularities belongs to upper half plane. Okay. We can also represent this complex number as e raised to minus pi I by 4, because this argument is uh, positive direction, it is 5 pi by 4. So this argument is minus pi by 4, right? So we can write this as e raised to minus pi by 4. Similarly, we can write this also. Oh, sorry, not this one. This argument is 7 pi by 4, right? This argument is 7 pi by 4. So this portion is minus pi by 4. So we can write this as e raised to minus I pi by 4. Okay. Similarly, we can write this as e raised to minus 3 pi I by 4. Okay. Because if this argument is 5 pi by 4, so this portion is 3 pi by 4. Like that. Then what is the residue corresponding to e raised to pi I by 4 of our function 1 by 1 plus z raised to 4? It is clear that here our function is of the form sum p of z by q of z. Okay, and all the singularities are simple. Okay, so by a, by a previous case, we know that its residue is of the form p of z naught by q dash of z naught. We have a standard formula for calculating residue of functions like this: p of z by q of z, and z naught is a symbol 0 of denominator. Okay, so here residue is equal to 1 by, what is the derivative of denominator? That is 4 z raised to 3 at e raised to pi I by 4. So this is equal to 1 by 4 raised to 3, e raised to pi I by 3 raised to 3, that is e raised to 3 pi I by 4. Okay, this can be written as 1 by 4 times, and what about 3 pi by 4? We can write 3 pi by 4 as pi minus pi by 4. This is 3 pi by 4. So this is e raised to pi minus pi by 4 times I. So this is equal to 1 by 4 e raised to pi I times e raised to minus pi by 4 I. And what about e raised to pi I? E raised to pi I is minus 1. So this is minus 1. So minus 1 by 4, and e raised to, this become e raised to pi I by 4. So minus e raised to pi I by 4 by 4. So this is residue at first pole. Similarly, we have to find the residue at the second pole. Okay, similarly, the residue at z is equal to e raised to 3 pi I by 4 of the function 1 by 1 plus z raised to 4 is equal to, using the same rule, p of z by q dash of z, p of z naught by q dash of z naught. So 1 by 4 z raised to 3, the derivative of this denominator, and z is equal to e raised to 3 pi I by 4. Okay, when we substituting z is equal to this value, this become 1 by 4 times, this is raised to 3. So this 3 into 3 become 9. So e raised to 9 pi I by 4. And what about this 9 pi I by 4? We know that 9 pi by 4 can be written as 2 pi plus pi by 4. Okay, so this become 1 by 4 times e raised to 2 pi plus pi by 4 times I. Okay, so this is equal to 1 by 4 times e raised to 2 pi I into e raised to pi by 4 I. What about e raised to 2 pi I? That is cos 2 pi plus I sin 2 pi, and cos 2 pi is 1, sin 2 pi is 0, so this is 1, this become 1, and this is e raised to minus pi by 4 I. Okay, so the residue is e raised to minus pi by 4 I divided by 4. Okay, so this is residue at z1, this is residue at z2. Okay, so this integral is equal to 2 pi I into sum of the residues of the singularities lying in the upper half plane. So sum of these two. So this is residue at z1, that is minus e raised to pi I by 4. Okay, there is a space problem, so we consider here. So this is equal to 1 by 2, and this portion become 2 pi I into sum of the residues where for the poles belongs to upper half plane. So these are the residues corresponding to poles belongs to upper half plane. So this is the first residue, it is minus e raised to pi I by 4 by 4 plus e raised to minus pi I by 4 by 4. Okay, so this is equal to, we can cancel these two, and one 4 is common, take outside. So this is pi I by 4 times e raised to minus pi I by 4 minus e raised to minus pi I by 4. Sorry, this is minus e raised to pi I by 4. So this is pi I by 4. Okay. So again we can rearrange this like this by taking a minus sign outside. So this become minus of pi I by 4 into e raised to pi I by 4 minus e raised to minus pi I by 4. Now this is of the form e raised to theta minus e raised to minus e raised to theta minus e raised to. Now this is of the form. Now this is of the form e raised to I theta minus e raised to minus I sin theta. Sorry, this is e raised to I theta minus e raised to minus I theta. Okay, that is e raised to form e raised to I theta minus e raised to minus I theta. This is nothing 2I sin theta, right? So this become minus pi I by 4 2I sin pi by 4, and this is equal to, okay, this I into I become minus 1, so there is a one more minus sign, so this become plus, and this is pi, and we can cancel these 2 and 4, so this become pi by 2 into sin pi by 4. What is sin pi by 4? That is 1 by root 2. So this is equal to pi by 2 root 2. So integral 0 to infinity dx by 1 plus x raised to 4 is equal to pi by 2 root 2. Okay. Yes, the final answer is pi by 2 root 2. With this, we have covered all the topics of this course. So, with this lecture, we are winding up. Thank you for your kind cooperation. Okay, thank you once again. Thank you.